Imagine making a phone call to the other side of Earth while both of you are moving at thousands of miles per hour through space. It sounds impossible, yet every single day, billions of messages, GPS directions, television broadcasts, weather reports, and emergency signals travel through satellites orbiting far above our heads. Somehow, these spacecraft keep talking to Earth almost continuously. They rarely lose their connection. So how is that even possible? For decades, people assumed satellites simply floated overhead like giant radio towers in space. But scientists were stunned as satellite technology evolved into one of the most sophisticated communication systems humanity has ever built. The truth turned out to be far more complex than expected. The secret isn't stronger antennas. It isn't more powerful transmitters. It's an invisible network of physics, mathematics, and engineering working together every second. And once you understand how it works, you'll never look at the sky the same way again. Every satellite faces a problem that seems almost impossible. Space is enormous. A communication satellite may orbit nearly 22,000 miles above Earth in geostationary orbit, while others race around the planet every 90 minutes in low Earth orbit at nearly 17,500 miles per hour. Meanwhile, Earth itself is spinning. Clouds move. The atmosphere bends radio waves. Solar storms constantly bombard space with charged particles. Millions of wireless devices generate their own signals every second. Without protection, satellite messages would disappear inside this overwhelming ocean of noise. So engineers invented something remarkable. Instead of sending information only once, satellites encode every message using sophisticated error-correcting codes. These mathematical systems add carefully designed patterns into the transmission. If parts of the signal become damaged during its journey, computers on Earth can often reconstruct the missing information before anyone notices. It's almost like solving a puzzle with several missing pieces. The picture still becomes complete. This technology quietly protects everything from weather satellites to spacecraft exploring distant planets. And that's only the beginning. Because keeping a satellite connected isn't just about transmitting information. It's about knowing exactly when every signal should arrive.
That may sound like a small detail, but in satellite communication, timing is everything. Radio signals travel at the speed of light, about 186,000 miles per second. Even so, they still need time to cross the enormous distance between Earth and space. A signal to a geostationary satellite takes roughly a quarter of a second for a round trip. That tiny delay is enough to create echoes, dropped data, or failed connections if it isn't carefully managed. So before a single message is transmitted, every part of the network agrees on one thing: time. Modern satellites carry incredibly accurate atomic clocks or synchronize with ultra-precise timing from ground systems. Every transmission is stamped with exact timing information. Ground stations know precisely when a signal should arrive, and computers instantly recognize if anything is late, early, or missing. This synchronization allows millions of conversations, internet sessions, television broadcasts, and navigation signals to travel through space at the same time without becoming hopelessly tangled together. But timing is only half the battle. Imagine thousands of satellites trying to speak over one another at once. The result would be chaos. To prevent this, Engineers divided the invisible radio spectrum into carefully organized frequency bands. Different satellites, services, and regions are assigned specific portions of the spectrum. Advanced antennas also reuse frequencies by pointing separate beams toward different parts of Earth, allowing the same frequencies to carry different conversations hundreds of miles apart. It's an invisible traffic control system for radio waves. Without it, modern satellite communication would collapse. Even then, another threat constantly lurks above Earth: space weather. The Sun regularly releases powerful eruptions of charged particles known as solar storms. Scientists were stunned to discover that these storms can disturb Earth's magnetic field, interfere with radio transmissions, and even damage satellite electronics. To survive, satellites are built like miniature fortresses. Sensitive electronics are protected with radiation shielding. Backup computers stand ready if one system fails. Critical components are duplicated, so another can immediately take over if something goes wrong. Redundancy is the reason many satellites continue operating for years, even after individual components begin to wear out. And if one satellite can no longer provide coverage, the network often reroutes communication through another spacecraft before users even notice. That is perhaps the greatest secret of all. Most people imagine a single satellite connecting directly to a single user. The reality is far extraordinary. Today's communications depend on an enormous global network of satellites, ground stations, fiber optic cables, tracking systems, and automated computers working together every second. If one path becomes unavailable, another is often selected almost instantly. The connection doesn't survive because one machine is perfect. It survives because the entire system is designed to adapt. Now, that system is entering a completely new era. Low Earth orbit constellations containing thousands of satellites are creating a dynamic web surrounding our planet. Instead of relying on only a few distant spacecraft, data can hop rapidly from satellite to satellite using laser links traveling through the vacuum of space. Engineers solved an extraordinary challenge by turning thousands of independent spacecraft into a coordinated orbital network. The result is lower delay, greater reliability, and internet access reaching places that once seemed impossible to connect. And this technology won't stop at Earth. Future missions to the Moon and Mars will require entirely new communication networks capable of spanning millions of miles. Scientists are already developing systems that can automatically route information across deep space, creating the foundation for humanity's first true interplanetary internet. The mystery, then, was never about why satellites never lose signal. The real answer is that they never work alone. Every successful transmission is the result of astonishing precision, flawless timing, intelligent software, advanced physics, and thousands of engineers solving problems most people never even realize exist. The next time your GPS guides you home, your weather app updates in seconds, or a live video streams from the other side of the world, remember this: above your head, an invisible network is performing one of humanity's greatest engineering achievements, connecting an entire planet through the silent language of space.